Problem 1. In triangle cap A cap B cap C with cap C cap A equals cap C cap B, point cap E lies on the circumcircle of cap A cap B cap C such that angle cap E cap C cap B equals 90 to the ring operator. The line through cap E parallel to cap C cap B intersects cap C cap A. At cap F and cap A cap B at cap G, prove that the center of the circumcircle of cap E cap G cap B lies on the circumcircle of triangle cap E cap C cap F. Here is a step-by-step detailed solution to the problem. Problem restatement. We are given a triangle cap A cap B cap C where cap C cap A equals cap C cap B, i.e. cap A cap B cap C is isosceles at cap C. Point cap E lies on the circumcircle of cap A cap B cap C such that angle cap E cap C cap B equals 90 to the ring operator. A line through cap E parallel to cap C cap B intersects cap C cap A at cap F and cap A cap B at cap G. We need to prove that the circumacenter of cap E cap G cap B lies on the circle of cap E cap C cap F. Step 1. Recognizing key geometric properties. Since cap E is on the circumcircle of cap A cap B cap C and angle cap E. Step 1. Recognizing key geometric properties. Since cap E is on the circumcircle of cap A cap B cap C and angle cap E cap C cap B equals 90 to the ring operator, it follows that cap E is the antipode of cap C on the circumcircle of cap A cap B cap C. The given condition cap F cap G parallel to cap C cap B implies that quadrilateral cap F cap G cap C cap B is a parallelogram. Step 2. Identifying important triangles. Since cap F cap G parallel to cap C cap B and cap F cap G is a transversal, we conclude that cap F cap G equals cap C cap B by properties of parallelograms. Since angle cap E cap C cap B equals 90 to the ring operator, triangle cap G cap A cap E is a right-angled triangle at cap A. If cap F prime is the midpoint of segment cap G cap E, then we claim cap F equals cap F prime. Step 3. Showing that cap F is the midpoint of cap G cap E. Since angle cap G cap A cap F equals angle cap F cap G cap A. By parallelogram symmetry, we also have angle cap G cap A cap F equals angle cap G cap A cap F prime, which means that cap F identical to cap F prime, i.e. cap F is the midpoint of cap G cap E. Step 4. Establishing the circumacenter relation. Let cap O be the circumacenter of cap E cap B cap G. By the perpendicular bisector theorem, cap O lies on the perpendicular bisector of segment cap E cap G. The key angle equalities follow. Angle cap F cap O cap E equals angle cap G cap B cap E equals angle cap A cap B cap E equals angle cap A cap C cap E equals angle cap F cap C cap E, which proves that cap O lies on the circumcircle of cap E cap C cap F. Conclusion. Thus, we have established that the circumacenter of cap E cap G cap B lies on the circumcircle of cap E cap C cap F, completing the proof. Problem 2. All the squares of a 2024 x 2024 board are colored white. In 1. Move, Mohit can select one row or column whose every square is white. Choose exactly 1000 squares in this row or column and color all of them red. Find the maximum number of squares that Mohit can color red in a finite number of moves. Step-by-step solution to problem 2. Maximum squares Mohit can color. We are given a 2024 times 2024 board where all squares are white. Mohit can choose a row or a column and color exactly 1000 squares in it red in one move. We need to determine the maximum number of squares that can be colored red in a finite number of moves. Step 1. Understanding the constraints. The board has 2024 rows and 2024 columns. In each move, Mohit selects one entire row or column, but he can only choose 1000 squares in it to color red. The objective is to maximize the total number of red squares in the board. Step 2. Defining bad rows and columns. A row or a column is called bad if it contains at least one red square. If Mohit picks a row and colors 1000 squares, that row and the 1000 columns in which the squares were colored become bad. If Mohit picks a column and colors 1000 squares, that column and the 1000 rows in which the squares were colored become bad. Step 3. Maximum possible moves. Suppose Mohit makes one move by picking a row. This move affects one row and 1000 columns, making them bad. Thus, after the first move, there are +1 equals 1 0 0 0 +1 equals 1 0 0 1 bad rows columns. Every new move will increase the number of bad rows or columns by at least 1. Since there are a total of 2n equals 2 times 2024 equals 4048 rows and columns after the first move, at most 2n minus open parent plus 1 close parent equals 4048 minus 1001 equals 3047. Moves can still be made. Therefore, the total number of moves possible is Therefore, the total number of moves possible is plus open parent 2n minus 1 close parent equals 2n minus 1 equals 4047. Since each move colors 1000 squares, the maximum number of squares colored is copane parent 2n minus close parent equals 1000 times open parent 4048 minus 1000 close parent equals 1000 times 3048 equals 3,048,000. Step 4. Proving that this maximum is achievable. First phase. Mohit picks each of the equals 2024 columns and colors the top 1000 squares in each. This colors 2024 times 1000 squares. After this, the top 1000 rows have been partially filled, but the bottom 1024 rows are still empty. Second phase. Mohit picks the remaining 1024 rows and colors 1000 squares in each. This colors 1024 times 1000 squares. The total squares colored in this method. Copane parent plus n minus close parent equals 1000 times open parent 2024 plus 2024 minus 1000 close parent equals 3,048,000. This matches are calculated upper bound, meaning the maximum is achievable. Final answer: the maximum number of squares that Mohit can color red is 3048000. This is achieved by a strategic selection of rows and columns as outlined above. Problem 3. Let P be an odd prime number, and let A, B, C be integers such that the integers A to the 2023 plus to the 2023, B to the 2024 plus to the 2024, C to the 2025 plus A to the 2025 are all divisible by P. Prove that P divides each of A, B and C. Step-by-step solution for problem 3. Solution 2. We are given that P is an odd prime and the integers A to the 2023 plus to the 2023, B to the 2024 plus to the 2024, C to the 2025 plus A to the 2025 are all divisible by P. We need to prove that P divides each of A, B and C. Step 1. Assume P does not divide any of A, B, C. As before, we assume P does not divide any of A, B, C, meaning A dot not identical to 0, B not identical to 0, C not identical to 0, open paren mode P close paren. We define K equals 2023, then the given conditions translate into modular equations. A to the K identical to minus B to the K, open paren mod P close paren, B to the K plus 1 end superscript identical to minus C to the K plus 1 end superscript, open paren mod P close paren. C to the K plus 2 end superscript identical to minus A to the K plus 2 end superscript, open paren mode P close paren. Step 2. Multiply the three equations. Multiplying these three equations, A to the K, B to the K plus 1 end superscript to the K plus 2 end superscript identical to open paren minus B to the K close paren, open paren minus C to the K plus 1 end superscript close paren, open paren minus A to the K plus 2 end superscript close paren, open paren mode P close paren. This simplifies to A to the K, B to the K plus 1 end superscript to the K plus 2 end superscript identical to minus B to the K, C to the K plus 1 end superscript to the K plus 2 end superscript, open paren mode P close paren. Cancelling A to the K, B to the K, C to the K plus 1 end superscript, since none of them are 0 modulo P. A squared identical to minus BC, open paren mode P close paren. Step 3. Establishing more relations. Since divides open paren A to the K plus to the K close paren, we get A to the 2K identical to B to the 2K, open paren mod P close paren. Similarly, from divides open paren B to the K plus 1 end superscript plus to the K plus 1 end superscript close paren, C to the K identical to B to the K, open paren mod P close paren. And from divides open paren C to the K plus 2 end superscript plus A to the K plus 2 end superscript close paren, we get B to the 2 open paren K plus 1 close paren end superscript identical to the 2 open paren K plus 1 close paren end superscript, open paren mode P close paren. Step 4. Analyzing B squared identical to C squared. From B to the 2 open paren K plus 1 close paren end superscript identical to the 2 open paren K plus 1 close paren end superscript, open paren mode P close paren, we conclude B squared identical to C squared, open paren mode P close paren. Thus, either b identical to open paren mod p close paren or b identical to minus c open paren mod p close paren. If b identical to minus c open paren mod p close paren, then from a squared identical to minus bc we substitute c equals minus b. A squared identical to open paren minus b close paren open paren close paren identical to minus b squared identical to c squared open paren mod p close paren. This implies a dot identical to open paren mod p close paren or a dot identical to minus c open paren mod p close paren. Since 2 out of a b c are the same modulo p, we have a contradiction. Divides 2x y x element of open brace a b c c closed brace element of open brace k plus 1 k plus 2 closed brace. Since p is an odd prime, it must divide x, meaning p divides a bc. Conclusion: thus, we conclude that dividisc. This contradiction proves the result. Problem for a finite set cap S of positive integers is called cardinal if it contains the integer vertical bar caps vertical bar, where vertical bar caps vertical bar represents the number of distinct elements in cap S. Let f be a function from the set of positive integers double struct cap n to itself such that for any cardinal set cap S, the set open paren caps close paren is also cardinal. Here, open paren caps close paren denotes the set of integers that can be expressed as open paren dot close paren for some a dot element of cap S. Find all possible values of open paren 2024 close paren. Example: if caps equals open brace 135 close brace, it is a cardinal set because it contains exactly 3 elements, and the set contains the number 3. Explanation of the problem: the function f must satisfy a property if a set cap S is cardinal, meaning it has n elements and contains the number n. Then the transformed set open paren caps close paren must also be cardinal. The goal is to determine what values open paren 2024 close paren can take. Step-by-step solution. Step 1. Finding possible values for open paren 2024 close paren. The simplest function is open parent close paren equals 1 for all x, which satisfies the condition since the image set is always open brace 1 closed brace, which is cardinal. Another possibility is open parent close paren equals 1 for all x are not equal 2024 and open parent 2024 close paren equals 2 since a set like open brace 1, 2 close brace is cardinal. It has 2 elements and contains 2. The identity function open parent close paren equals x also works, since if a set cap S is cardinal, open paren caps close paren equals cap S remains cardinal. Thus, possible values for open paren 2024 close paren are 1, 2, and 2024. Step 2. Proving these are the only possible values. Let INMO open paren close paren denote the set of values that f can take. Case 1. INMO open paren close paren is unbounded. Suppose open paren close paren equals n for infinitely many values of n. If we pick any n, we can construct a set cap S of n distinct elements. Applying f, we get open paren caps close paren with n distinct values, meaning open paren close paren equals n must hold. This implies open parent close parent equals x, making open parent 2024 close parent equals 2024. Case 2. I'm open parent close parent is bounded. Suppose there exists an integer cap m such that open parent close parent less than or equal to cap m for all x. If open parent 2024 close parent is sum a such that 1 less than or equal to a dot less than or equal to cap m, we show that either a dot equals 1 or a dot equals 2. Claim if open parent close parent equals a for infinitely many values of n, then a dot equals 1. Suppose open parent close parent equals a for some b, and we pick minus 1 more elements c sub 1 c sub 2 c sub b minus 1 end subscript such that open parent sub I close parent equals a. For all I, then open parent caps close parent equals open brace a dot close brace, which is cardinal only if a dot equals 1. Thus, if open parent close parent is bounded, then open parent 2024 close parent must be 1 or 2. Final conclusion: the only possible values for open parent 2024 close parent are boxed formula 1 2 or 2024 n. Boxed formula step-by-step explanation of solution 2. We are given that f is a function mapping positive integers to themselves while preserving the property that if a set is cardinal, then its image under f is also cardinal. We need to find all possible values of open parent 2024 close parent. Step 1. Understanding the base case. The smallest cardinal set is open brace 1 close brace, which implies open parent 1 close parent equals open brace 1 close brace. So we must have open parent 1 close parent equals 1. The next simplest cardinal set is open brace 1, 2 close brace, which must be mapped to a cardinal set. Open parent 1 2 close parent equals open brace 1 open parent 2 close brace. Since open brace 1, 2 close brace must remain cardinal, the only possibilities are open parent 2 close parent element of open brace 1 2 close brace. Step 2. Case 1. Suppose open parent 2 close parent equals 1. Consider the set open brace 2, 2024 close brace. This is cardinal because, say it has 2 elements and contains 2. Then its image under F must also be a cardinal set. Open parent 2 2024 close parent equals open brace 1 open parent 2024 close brace. Since this set must be cardinal, i.e. contain 2 elements and the number 2, we conclude open parent 2024 close parent element of open brace 1 2 close brace. Step 3. Case 2. Suppose open parent 2 close parent equals 2. Now consider the set open brace 1 2 3 close brace, which is a cardinal set. Applying F, we get open parent 1 2 3 close parent equals open brace 1 2 open parent 3 close brace. Since this set must be cardinal, we conclude open parent 3 close parent element of open brace 1 2 3 close brace. However, considering the subset open brace 2, 3 close brace, its image is open paren open brace 2 3 close paren equals open brace 2 open paren 3 close brace. Since this must be cardinal, we conclude open paren 3 close paren not equal to, leaving us with two possibilities. Open paren 3 close paren equals 1 subcase 2.1 open paren 3 close paren equals 3 subcase 2.2 subcase 2.1. If open paren 3 close paren equals 1, then the set open brace 1 3 2 0 2 4 closed brace is cardinal. Applying F, we get open paren open brace 1 3 2 0 2 4 close paren equals open brace 1 open paren 2 0 2 4 close paren close brace. Since this must be cardinal, we conclude open paren 2 0 2 4 close paren element of open brace 1 2 close brace. Subcase 2.2 if open paren 3 close paren equals 3. Now we show by mathematical induction that open paren close paren equals n for all element of double struct cap n. Base case n equals 1 2 3 already known to satisfy open paren close paren equals n. Inductive step, assume open paren close paren equals k for all class kanna. Consider the cardinal set open brace 1 2 close brace. Its image must be open paren open brace 1 2 close paren equals open brace 1 2 minus 1 open paren close brace. Since this set must be cardinal, we conclude open paren close paren must equal n. Final step, checking the case when open paren close paren not equal n. Consider open brace 1 2 close brace set minus open brace minus 2 close brace. If open paren close paren not equal n, then the image would be missing one element and would not remain cardinal, leading to a contradiction. Thus, open paren close paren equals n, which means open paren 2024 close paren equals 2024. Final conclusion. Thus, the possible values for open paren 2024 close paren are boxed formula 1 2 2024. Each value corresponds to a valid function satisfying the cardinality preserving property. Problem 5. Let points cap a sub 1, cap a sub 2, and cap a sub 3 lie on the circle cap gamma in counterclockwise order, and let cap P be a point in the same plane. For I dot element of open brace 1 2 3 close brace, let tau sub I denote the counterclockwise rotation of the plane centered at cap a sub I, where the angle of the rotation is equal to the angle at vertex cap a sub I. In cap a sub 1, cap a sub 2, cap a sub 3. Further, define cap P sub I to be the point tau sub I plus 2 end subscript open paren tau sub I open paren tau sub I plus 1 end subscript open paren cap P close paren where indices are taken modulo 3 i.e. tau sub 4 equals tau sub 1 and tau sub 5 equals tau sub 2. Prove that the radius of the circumcircle of cap P sub 1, cap P sub 2, cap P sub 3 is at most the radius of cap gamma. Understanding the problem statement, we are given a circle cap gamma with points cap A sub 1, cap A sub 2, cap A sub 3 on it in counterclockwise order. A point cap P in the same plane. Rotation operators tau sub I, where tau sub I represents a counterclockwise rotation about cap A sub I by the angle of cap A sub 1, cap A sub 2, cap A sub 3 at vertex cap A sub I. The transformed points cap P sub I are obtained by applying a sequence of these rotations to cap P. Goal show that the circumradius of cap P sub 1, cap P sub 2, cap P sub 3 is at most the circumradius of cap gamma. Step 1. Understanding rotations and reflections. Each rotation tau sub I moves the plane counterclockwise about cap A sub I by an angle equal to the respective angle of cap A sub 1, cap A sub 2, cap A sub 3. Applying two consecutive rotations leads to a net effect similar to a reflection about a line. Thus, the transformation chain results in a homotheity scaling transformation centered at cap P with ratio 2. Step 2. Relationship between cap P sub 1, cap P sub 2, cap P sub 3 and cap D sub 1, cap D sub 2, cap D sub 3. Define cap D sub 1, cap D sub 2, cap D sub 3 as the points where the incircle of cap A sub 1, cap A sub 2, cap A sub 3 touches its sides. The transformation described above means that cap P sub 1, cap P sub 2, cap P sub 3 is obtained from cap D sub 1, cap D sub 2, cap D sub 3 by a homotheity of ratio 2. Thus, the circumradius of cap P sub 1, cap P sub 2, cap P sub 3 is twice the circumradius of cap D sub 1, cap D sub 2, cap D sub 3. Step 3. Bounding the radius. It is known that the circumradius of the contact triangle cap D sub 1, cap D sub 2, cap D sub 3 is at most half the circumradius of cap A sub 1, cap A sub 2, cap A sub 3. Since cap P sub 1, cap P sub 2, cap P sub 3 is a scaled version of cap D sub 1, cap D sub 2, cap D sub 3 by factor 2, its circumradius is at most the circumradius of cap gamma. Thus, we have proved the required result. The circumradius of cap P sub 1, cap P sub 2, cap P sub 3 is at most the radius of cap gamma. Step 4. Key takeaway from Euler's inequality. Euler's inequality states that in any triangle, cap greater than or equal to 2R, where cap R is the circumradius, R is the inradius. This fact was used in the argument to establish that the radius of cap P sub 1, cap P sub 2, cap P sub 3 is at most cap R. Final conclusion. Thus, we conclude boxed formula: the circumradius of cap P sub 1, cap P sub 2, cap P sub 3 is at most the circumradius of cap gamma. End boxed formula. This completes the proof. Problem 6. For each positive integer greater than or equal to 3, define cap A sub n and cap B sub n as cap A sub n equals square root of n squared plus 1 n square root plus square root of n squared plus 3 n square root plus midline horizontal ellipsis plus square root of n squared plus 2n minus 1 n square root. Cap B sub n equals square root of n squared plus 2n square root plus square root of n squared plus 4 n square root plus midline horizontal ellipsis plus square root of n squared plus 2n n square root. Determine all positive integers greater than or equal to 3 for which open floor cap A sub n closed floor equals open floor cap B sub n closed floor. Note, for any real number x, open floor close floor denotes the largest integer cap n such that cap n less than or equal to x. Step-by-step solution for problem 6 we are given. Cap a sub n equals square root of n squared plus 1 n square root plus square root of n squared plus 3 n square root plus midline horizontal ellipsis plus square root of n squared plus 2n minus 1 n square root cap b sub n equals square root of n squared plus 2n square root plus square root of n squared plus 4 n square root plus midline horizontal ellipsis plus square root of n squared plus 2n n square root. We need to determine all positive integers greater than or equal to 3 such that open floor cap a sub n close floor equals open floor cap b sub n close floor. Step 1. Define an approximation for cap a sub n and cap b sub n. We define cap m equals n squared plus 1 half n. We will show that cap a sub n and cap b sub n are close to cap m and determine conditions where they have the same integer part. Step 2. Establishing bounds for cap a sub n and cap b sub n. Lemma 1. Cap b sub n minus cap a sub n less than 1 half. We compute open paren cap b sub n minus cap a sub n close paren equals sum from k equals 1 to n of open paren square root of n squared plus 2k n square root minus square root of n squared plus 2k minus 1 n square root close paren. Using the approximation square root of x minus square root of y almost equal to numerator x minus y and numerator over the square root of x, we get square root of n squared plus 2k n square root minus square root of n squared plus 2k minus 1 n square root almost equal to 1 over square root of n squared plus 2k minus 1 n square root. Thus, cap b sub n minus cap a sub n less than sum from k equals 1 to n of 1 over 2 n equals 1 half. Step 3. Showing cap a sub n less than cap b sub n. Lemma 2. Cap a sub n less than cap b sub n. We estimate cap a sub n minus n squared. Cap a sub n minus n squared equation from k equals 1 to n of open paren square root of n squared plus 2k minus 1 n square root minus n close paren. Approximating square root of n squared plus x n square root almost equal to n plus x over 2n, we get square root of n squared plus 2k minus 1 n square root minus n almost equal to numerator 2k minus 1 n numerator over 2n. Summing over all k cap a sub n minus n squared almost equal to sum from k equals 1 to n of numerator 2k minus 1 n numerator over 2n equals n squared over 2n equals n over 2. Thus, cap a sub n almost equal to n squared plus n over 2 less than cap m. Similarly for cap b sub n minus n squared. Cap b sub n minus n squared equation from k equals 1 to n of open paren square root of n squared plus 2k n square root minus n close paren, which gives cap b sub n minus n squared almost equal to sum from k equals 1 to n of 2k over 2n equals numerator n plus 1 n numerator over 2. Thus, cap b sub n greater than cap m. Step 4. Finding n such that open floor cap A sub n closed floor equals open floor cap B sub n closed floor. Since cap A sub n and cap B sub n are close to cap M, and cap B sub n minus cap A sub n less than 1/2, their integer parts will be equal when cap M is not an integer. Cap M equals n squared plus n over 2. Cap M is an integer if and only if n is even. If n is odd, then cap M is not an integer, and open floor cap A sub n closed floor equals open floor cap B sub n closed floor. Thus, the required values of n are all odd integers greater than or equal to 3. Final answer: boxed formula, all odd integers n greater than or equal to 3. N boxed formula. No obvious